An indoor positioning system is a system to locate objects or people inside a building using radio waves, magnetic fields, acoustic signals, or other sensory information collected by mobile devices. There are several commercial systems on the market, but there is no standard for an IPS system. IPS systems use different technologies, including distance measurement to nearby anchor nodes, magnetic positioning, dead reckoning. They either actively locate mobile devices and tags or provide ambient location or environmental context for devices to get sensed. The localized nature of an IPS has resulted in design fragmentation, with systems making use of various optical, radio, or even acoustic technologies. System designs must take into account that at least 3 independent measurements are needed to unambiguously find a location. For smoothing to compensate for stochastic errors, there must be a sound method for reducing the error budget significantly. The system might include information from other systems to cope for physical ambiguity and to enable error compensation. Applicability and precision. Due to the signal attenuation caused by construction materials, the satellite-based global positioning system loses significant power indoors, affecting the required coverage for receivers by at least 4 satellites. In addition, the multiple reflections at surfaces cause multipath propagation, serving for uncontrollable errors. These very same effects are degrading all known solutions for indoor locating, which uses electromagnetic waves from indoor transmitters to indoor receivers. A bundle of physical and mathematical methods is applied to compensate for these problems. Promising direction radio frequency positioning error correction opened by the use of alternative sources of navigational information, such as inertial measurement unit, monocular camera simultaneous localization and mapping, and Wi-Fi SLAM. Integration of data from various navigation systems with different physical principles can increase the accuracy and robustness of the overall solution. With detailed reading in the marketing documents and even in the specifications served by many of the IPS vendors, the interested customer will look for details on precision, reproducibility and other terms for quality of function with little success. Many vendors do not even tangle with the term accuracy. Relation to GPS, global navigation satellite systems are generally not suitable to establish indoor locations, since microwaves will be attenuated and scattered by roofs, walls and other objects. However, in order to make positioning signals ubiquitous, integration between GPS and indoor positioning can be made. Currently, GNSS receivers are becoming more and more sensitive due to ceaseless progress in chip technology and processing power. High-sensitivity GNSS receivers are able to receive satellite signals in most indoor environments, and attempts to determine the 3D position indoors have been successful. Besides increasing the sensitivity of the receivers, the technique of AGPS is used, where the almanac and other information are transferred through a mobile phone. However, proper coverage for the required 4 satellites to locate a receiver is not achieved with all current designs for indoor operations. Beyond, the average error budget for GNSS systems normally is much larger than the confinements, in which the locating shall be performed. Locating and positioning, despite the name, most current IPS systems are so coarse that they cannot be used to detect the orientation or direction of an object. Locating and tracking, one of the methods to thrive for sufficient operational suitability is tracking. Whether a sequence of locations determined form a trajectory from the first to the most actual location. Statistical methods then serve for smoothing the locations determined in a track resembling the physical capabilities of the object to move. This smoothing must be applied, when a target moves, and also for a resident target, to compensate erratic measures. Otherwise the single resident location or even the followed trajectory would compose of an itinerant sequence of jumps. Identification and segregation. In most applications the population of targets is larger than just one. Hence the IPS must serve a proper specific identification for each observed target and must be capable to segregate and separate the targets individually within the group. An IPS must be able to identify the entities being tracked, despite the non-interesting neighbors. Depending on the design, either a sensor network must know from which tag it has received information, or a locating device must be able to identify the targets directly. Non-radio technologies can be used for positioning without using the existing wireless infrastructure. This can provide increased accuracy at the expense of costly equipment and installations. Magnetic positioning Magnetic positioning can offer pedestrians with smartphones an indoor accuracy of 1–2 meters with 90% confidence level, without using the additional wireless infrastructure for positioning. Magnetic positioning is based on the ion inside buildings that create local variations in the Earth's magnetic field. Unoptimized compass chips inside smartphones can sense and record these magnetic variations to map indoor locations. Inertial measurements Pedestrian dead reckoning and other approaches for positioning of pedestrians propose an inertial measurement unit carried by the pedestrian either by measuring steps indirectly or in a foot-mounted approach, sometimes referring to maps or other additional sensors to constrain the inherent sensor drift encountered with inertial navigation. Inertial measures generally cover the differentials of motion, hence the location gets determined with integrating and thus requires integration constants to provide results. The actual position estimation can be found as the maximum of a 2D probability distribution which is recomputed at each step taking into account the noise model of all the sensors involved and the constraints posed by walls and furniture. Wireless technologies Any wireless technology can be used for locating. Many different systems take advantage of existing wireless infrastructure for indoor positioning. There are three primary system topology options for hardware and software configuration: network-based, terminal-based, and terminal-assisted. Positioning accuracy can be increased at the expense of wireless infrastructure equipment and installations. Wi-Fi-based positioning system Wi-Fi positioning system is used where GPS is inadequate. The localization technique used for positioning with wireless access points is based on measuring the intensity of the received signal and the method of fingerprinting. Typical parameters useful to geolocate the Wi-Fi hotspot or wireless access point include the SSID and the MAC address of the access point. The accuracy depends on the number of positions that have been entered into the database. The possible signal fluctuations that may occur can increase errors and inaccuracies in the path of the user. AnyPlace is a free and open-source Wi-Fi positioning system that allows anybody to rapidly map indoor spaces and that won several awards for its location accuracy. Bluetooth According to the Bluetooth Special Interest Group, Bluetooth is all about proximity, not about exact location. Bluetooth was not intended to offer a pinned location like GPS, however is known as a geo-fence or micro-fence solution, which makes it an indoor proximity solution, not an indoor positioning solution. Micro-mapping and indoor mapping has been linked to Bluetooth and to the Bluetooth LE-based iBeacon promoted by Apple. Incorporated large-scale indoor positioning system based on iBeacons has been implemented and applied in practice. Choke point concepts Simple concept of location indexing and presence reporting for tagged objects, uses known sensor identification only. This is usually the case with passive radio frequency identification systems, which do not report the signal strengths and various distances of single tags or of a bulk of tags and do not renew any before known location coordinates of the sensor or current location of any tags. Operability of such approaches requires some narrow passage to prevent from passing by out of range. Grid concepts Instead of long-range measurement, a dense network of low-range receivers may be arranged, for example in a grid pattern for economy, throughout the space being observed. Due to the low range, a tag identity will be identified by only a few close, networked receivers. An identified tag must be within range of the identifying reader, allowing a rough approximation of the tag location. Advanced systems combine visual coverage with a camera grid with the wireless coverage for the rough location. Long-range sensor concepts Most systems use a continuous physical measurement along with the identification data in one combined signal. Reach by these sensors mostly covers an entire floor, or an aisle or just a single room. Short-reach solutions get applied with multiple sensors and overlapping reach. Angle of arrival Angle of arrival is the angle from which a signal arrives at a receiver. AOA is usually determined by measuring the time difference of arrival between multiple antennas in a sensor array. In other receivers, it is determined by an array of highly directional sensors. The angle can be determined by which sensor received the signal. AOA is usually used with triangulation and a known baseline to find their location relative to two anchor transmitters. Time of arrival time of arrival is the amount of time a signal takes to propagate from transmitter to receiver. Because the signal propagation rate is constant and known, the travel time of a signal can be used to directly calculate distance. Multiple measurements can be combined with trilateration and multilateration to find a location. This is the technique used by GPS systems, which used to generally require a complicated synchronization mechanism to maintain a reliable source of time for sensors. The accuracy of the TOA-based methods often suffers from massive multipath conditions in indoor localization, which is caused by the reflection and diffraction of the RF signal from objects in the environment. However, it is possible to reduce the effect of multipath by applying temporal or spatial sparsity-based techniques. Received signal strength indication Received signal strength indication is a measurement of the power level received by sensor. Because radio waves propagate according to the inverse square law, distance can be approximated based on the relationship between transmitted and received signal strength, as long as no other errors contribute to faulty results. The inside of buildings is not free space, so accuracy is significantly impacted by reflection and absorption from walls. Non-stationary objects such as doors, furniture, and people can pose an even greater problem, as they can affect the signal strength in dynamic, unpredictable ways. A lot of systems use enhanced Wi-Fi infrastructure to provide location information. None of these systems serves for proper operation with any infrastructure as is. Unfortunately, Wi-Fi signal strength measurements are extremely noisy, so there is ongoing research focused on making more accurate systems by using statistics to filter out the inaccurate input data. Wi-Fi positioning systems are sometimes used outdoors as a supplement to GPS on mobile devices, where only few erratic reflections disturb the results. Others radio frequency identification. Passive tags are very cost-effective, but do not support any metrics. Ultra-wideband, reduced interference with other devices, infrared, previously included in most mobile devices, Gen 2 IR, visible light communication, can use existing lighting systems. Ultrasound, waves move very slowly, which results in much higher accuracy. Mathematics, once sensor data has been collected, an IPS tries to determine the location from which the received transmission was most likely collected. The data from a single sensor is generally ambiguous and must be resolved by a series of statistical procedures to combine several sensor input streams. Empirical method one way to determine position is to match the data from the unknown location with a large set of known locations using an algorithm such as k-nearest neighbor. This technique requires a comprehensive on-site survey and will be inaccurate with any significant change in the environment. Mathematical modeling location will be calculated mathematically by approximating signal propagation and finding angles and or distance. Inverse trigonometry will then be used to determine location. Trilateration, triangulation, advanced systems combine more accurate physical models with statistical procedures, Bayesian statistical analysis, Kalman filtering. Uses. The major consumer benefit of indoor positioning is the expansion of location-aware mobile computing indoors. As mobile devices become ubiquitous, contextual awareness for applications has become a priority for developers. Most applications currently rely on GPS, however, and function poorly indoors. Applications benefiting from indoor location include augmented reality, school campus, guided tours of museums, shopping malls, store navigation, warehouses, airports, bus, train and subway stations, parking lots. Targeted advertising, social networking. Hospitals, hotels. Tourism. Sports. other public building maps. See also, automatic vehicle location, Bluetooth Smart, eCar Site Survey, Fuzzy Locating System, Internet of Things, GSM localization, Navizon, Near Field Communication, POINTR, Real-Time Locating System, Robotic Mapping, Sensor Fusion, Skyhook Wireless. References. External links, EZ localization, micro mapping in OpenStreetMap, indoor mapping in OpenStreetMap, indoor navigation SDK for mobile apps from IndoorS.